Hey everyone, welcome to another NLP video. Today we're looking at the paper FastFormers, Highly Efficient Transformer Models for Natural Language Understanding by authors from Microsoft. Transformer-based models have achieved state-of-the-art performance on a wide range of natural language understanding applications. One downside of these models is that they tend to be very large, requiring large amounts of memory, very big GPUs, and also they are very slow in terms of their inference performance. And this makes them prohibitive to use for industry applications that require low latency, fast inference, and in general low server costs. In this paper, they propose a new method called FastFormers, which is basically a set of recipes for drastically improving the efficiency of the transformer models in terms of inference time per second. And they want to make this efficiency improvement applicable for a wide range of natural language understanding tasks with the methods that they propose, which are quite a few of them. They're able to get up to 233x speed up compared to out-of-the-box models on CPU and up to 12x speed up on GPU with minimal loss of accuracy. This is quite a big improvement. So it's interesting to see what they have come up with. And also that they also claim that if you're using a Azure F16 whatever cloud instance, you're able to bring down your costs using their approach for 100 million requests from $4,000 to $18. So how do they do it? Let's jump straight into the details where they have a comparison of the various improvements that they propose. So in this table, you have the results. Basically, you have the methods as well as the improvements here. And we're looking at the time it took to basically go through the BoolQ validation dataset, which is, I believe, one of the tasks of the SuperGLUE dataset or so. So they're using always batch size 1 here, assuming that they are doing with some sort of a real-time inference situation. And all performance are measured on an Azure F16s V2 cloud instance. So they have the time, the cumulative speedup versus the baseline model without any optimizations, the speedup, the accuracy of the updated model, and then the estimated cost of running 100 million queries in terms of dollars. As a baseline, they have basically a PyTorch out-of-the-box transformer models. This could be either a Roberta or a BERT model with 12 layers, 768 dimension. This is the BERT base model or Roberta base. I think they test both architectures in the paper with similar results, I believe. This one takes 700 seconds and costs $4,200 to run 100 million queries. Then you have all the different optimizations that the authors talk about in the paper. The first optimization is to use a dynamic sequence length. So as you may be aware, the transformer models typically have a fixed sequence length, which is 512, meaning no matter what type of sequence you input, the sequence could be 50 or it could be 300. The sequence will always be padded up to 512. And because this is the way it has been programmed, the model has been trained with 512. So even if you have very short sequences, you're always going to end up running the computation for 512 steps, which is obviously a limitation for inference time. It would be ideal to be able to do this dynamically to save up on some computation, and this is precisely what the authors do with this dynamic sequence length approach, basically using a flexible sequence length, which brings down the time 3 times. So you're getting a 3.5x speed up already from this one, while maintaining the same accuracy and bringing down the cost. Another technique that they use is knowledge distillation. The idea of knowledge distillation is that you use your big model and then you try to train a distilled version of that model, basically using the signal, the outputs of the large model, the teacher model, to train the small model, which in this case is a 4-layer 312 transformer model. So you use the outputs of the large model to basically try to train the small model to behave the same as a large model. This is a technique invented a few years ago that has been shown to be quite effective at reducing the size of various deep learning models, and it seems to be effective also here, resulting in a further 32x speed up, while actually the model is achieving the same accuracy as the original model, which is quite nice. Another technique that they apply on top of that, in combination with all the other ones, is the quantization to 8 bits. So basically the models by default run on 32 bits. However, if you go to 8-bit, you are obviously going to be getting some memory efficiency, which allows you to basically increase your batch size or so, and to be able to process longer sequences, stuff like that, and speed ups. So they are using some sort of specialized libraries to basically quantize the distilled version of the models to go to 8-bit, which results in even faster time execution and speed up of 73x in total, and the individual speed up is 2x. And this results in some small loss in accuracy, but it's a very minor, about 0.6 here. And then another one that they do is, they also do some graph optimization techniques that you can read more about in the paper. Basically optimize the graph computation to get some further speed up. Another one is to try to do some parallelization. As I mentioned, this is all done on CPU here. So basically they try to come up with some methods to parallelize those models on those CPU threads even more, leading to a cumulative speed up of 129x, and this one is getting like 1.76 speed up for the best model, while leaving the accuracy unchanged from a previous one. And then a final optimization that they do is called structured pruning. So the basic idea of that one is they try to identify parts of the model which are least important, and then they can be pruned. And they try a bunch of techniques in the paper, but basically, let's say the best one that they come up with is removing 25% of the heads and 25% of the hidden states of the distilled model furthermore. And basically this is done by detecting parts of the network which seem to be contributing the least to the final prediction. And then I think they also do some fine-tuning of those pruned models. And this actually results to some further cumulative speed up to 178x or even 233x when you are pruning even more of the parameters of the network. And the final accuracy is reduced only also again a few points, but not a lot at all. So the worst quote unquote model is achieving accuracy of 72.81. And impressively, so this is in total, as I said, 233x. And the cost, if you look at the cost per 100 million queries, this is like also quite a significant cut, especially taking into account only the small number of accuracy that you lose with this, all of these optimizations that you try out. So this is quite cool, and as I said, you also get some speed ups on GPU as well. But on CPU, this is actually quite impressive that you can get up to 233x speed up, I gotta say. And I think this is the main parts that I wanted to cover from this paper. If you want to read more about the specific techniques that are employed, you can find the details in the paper. And as I said, looking forward to testing this model in action using the Hugging Face library. And also one maybe comment about this, I would say, I mean, this is actually quite nice because, yeah, we're getting these huge networks recently, right? And it would be great to get them down in terms of number of parameters and so on and so forth. So really looking forward to having more of those techniques popping up. But one thing that comes to mind actually is I'm wondering for this method, okay, this task, I'm not sure if this will be also applicable if we go to some more complicated tasks like text summarization or machine translation. Is it really possible to still get up to such huge improvements of 230x also for those much more complicated tasks, or is this reserved to these smaller tasks, basically involving some classification, which are also can be quite tricky, especially if you want to do all of them at the same time, but obviously they are a little bit simpler. So that is all that I wanted to cover for today. Thanks for watching, and please like and subscribe, and I'll talk to you in the next video.